So, results. So we are coming to the interpretive part of the section. So we have been gone through the general introductory part and how we could mathematically formalize the things, the conceptual and philosophical aspects of quantum mechanics. Now, the I would say we're coming to the cream of milk, or the rather the shake is ready for the interpretive aspects of those conceptual and mathematical or general considerations of quantum mechanical way the way base has been set up. So in that sense, if we will talk of interpretations, because when we talk of interpretations, it means that there is a scope or by which you can maneuver. There is a scope of interpreting. Interpretations means you can just there is scope to interpret things conceptually in more than one ways, or depends uniquely on from the vantage point of an observer, a quantum observer, how he is going to measure things or how he is going to record or register things. So before how we can have a quantum mechanical way of interpretations which have which have various subtleties, we can have brief comparison of classical and uh, quantum mechanical statistics. The statistics you can say is that, for example, so in classical physics, we have parameters Q, P, and in Hamiltonian equations, you have parameters Q and conjugate parameters Q and P, position and momentum, and time. So given a value, uh, so if we have parameters like Q1, Qn, and P1, Pn, and this is the time given the value, we can have value of Q0 and P0 at t, and we should have general physical laws. And what has to be determined is value of u naught of every entity concerned at time t naught. In the same way, this is third. Fourth is value of qt and pt of q and p at t. So you have at general t. And you can also have the fifth is value of u at any entity u of time t. So here either we have position and momentum, either we have position momentum conjugate. So we have in a given unique the position or momentum variable may might have a given unique eigenvalues which might be basically the probability distributions of q's and qp's in that sense. So here it's better to define q as function of t at q naught p naught. Pt can be defined as function of t at q naught p naught, and u can be defined as conjugate q t and pt together. So you can have qt, pt, and u as a function. So you can have these equations. So I'll write it here because they might be required. So they are 1, 2, and 3. So these are three equations of Qt in terms of this thing, because we might require them later. P0, Pt is K0, P0, and the conjugate is defined like this of Qt, Pt. So now if we have give this thing, so these relations will show that there is some problem in how causality, which will see how we can say causality vis-a-vis the statistical methods, because these if we write distributions at time t, distributions at time t, distributions at time t, not in the form d naught q, d naught p, and d naught qp. So we can have probability distributions of this position, momentum, and the position and momentum as a conjugate variable together. You can write them as probability, and this is the probability of combinations of q and p together. And you can say that they are the derivative of classical statistical physics. Now, what's the subtlety? Subtlety is that for example, you can given a one probability distributions QP at time t naught, and given physical laws. So we have to be what has to be determined is probability distributions d0q and d0p of every entity concerned at time t naught. The fourth is probability distributions at time dt q of p. The fifth is probability distribution. So either you can have distributions of two entities together at a given time, or you can have a probability of position and momentum separately. So you can have dtq and dtp as probability distributions, dtu of every other entity concerned at any time. So for a strict causal case, for a strict, if causality is not somehow causality is taken as given, or strict causality is restored, so so occurrence of probability distributions involves a further distinction that or so you can, if you causality is taken as a distinct thing, so occurrence of probability is also depend upon d0. So how you initial the way I said in the frequentistic interpretation of probabilities, there was a subtlety, the initial conditions, how we determine them. So so they had subtleties that the physical considerations can become important in determining the initial conditions also. In the frequentistic interpretation, the more number of what I should say random if we repeat a given choice of experiments, if we arrive at a given value, that is considered to be the most probable value. But the initial conditions, the thing is, the point is that if you, the initial d0, it's also choice of D0, it's also a what I should say, it involves a further distinctions on D0, P0. So for example, if we have D0Q as D0, in the same sense D0P as yes. So you can say in this sense, it's important to realize the determination cannot be reversed. Yes. So if we have independent entities like D0QP is equal to D0Q into D0P. So we can have this is by the application of theorem of spatial multiplication. If they are equation 6, 5 and 4, they are 1, 2 and 3. So the point is that the determination of combined determination of this P and Q, it's not as if we can determine P and Q separately. So combined probability distribution is not same as if you are determining the individual probability parameters of Q and P separately. So that's it. So it has bearing on how we can visualize or understand how can contextualize causality here. The probability distributions of Q and P together and pinning the probability distributions of these parameters separately. These two statements are not same. So if we have a causal law which should determine these, so the way we classical mechanics, you have P and Q. So how we can generate Liouville's theorem in that sense. So if you have QP in a given phase space, how we can map a given phase space to the phase space, which is, and there is something constant, it is something, so you arrive at a given phase space, its evolution in space time, and the mapping is there. So in the same way we can have a probability distribution, you can say that there are Q and P as a set as a parameters which depends upon D0 QP. You can say is D of Q1 Qn0 and P1 Pn0. This is one thing. You can take it 7. So for the this is at time t, for the values at time t for a general function f, you can have q1 is q1, q0, qn0, p1, pn0. In the same way, q2 can be q2, q10, qn0, p10 and pn0. And for pn, this is one is qn function, another is pn. You can have pn, q10, qn0, p1, pn0. So the point is that if we want to solve this by we can introduce the variables p1, and you can have probability distributions which involve the integration of variables vis-a-vis those integrals. So we can have a determinant delta, which we can define as delta can be defined as delta as dq0 by dq1 dpn0 by, so this is dq0 by dq1 dp0 by dq1. Now the second is so on and so three, and dq0 by the last one is dpn, and dpn by dpn0 by dpn, such that dtqp can be written as d of q1 qn p1 pn, or it's equivalent to d of q1 0 qn 0 p1 0 pn 0 multiplied by some determinant, which you can say for canonical parameters q and p. Yes. And for delta is equal to 1, we arrive at a theorem. So for an Hamiltonian equation, so we arrive at a what I should say, Liouville's theorem. So in the same way, we can have dtu can be determined, but we can omit the possibility of the subscript t, such that if u is defined as f of q1 qn p1 pn, so you can have this is 7 8 9 and this is 10, this is 11, yes, this is 8 and this is 8. So the point which we want to come to close is that we want to write whatever we have just written here in some symbolic form, because we have previously also continuously introduced these positions, momentum. So we had in quantum mechanical language, we had associated them with functions, or we had associated operators operating on those functions, and those functions had some values, eigenvalues associated to each eigenfunction, which was acted upon by some operator. So now these position and momentum functions, whether together or separately, because we have attached a probability distribution to those parameters in phase space, or the way we arrived at this, what I should say, in the limiting case, we arrived at Liouville's theorem. So there was a sort of conservation associated with it. So the question is, so if we associate probability with these parameters, can we see conservation of probabilities in that sense or not? So this is also a question. So what we are going to see the functional aspect of the thing, that so without specifying the individual forms of operators, we can have dtp p qp is f of operator. This is what I was saying. We are going to associate operators with these parameters. So d of t q is f operator d of t qp is equal to f operator p d0 qp, or dtp is f operator dtqp is f operator t, it's d0 qp. And now the last one, which is, so we have written it in terms of function u. U is the both p and q together. This one. Okay. Yes, yes. How we can write it like this? F operator d of t q of p is equal to f operator t d0 qp. Now further we can so what you can say, this is a case of a strict causal case, and this one. So we can say 15 and 17. So if we have this is 14, 15, 16, and 17. 15 and 17 represent 15 and this represent a generalization of first and 3. First and 3. 15 and 17. 15 and 17. This is 17. You can say it's. So we have the operator correspondence with the probability distributions. It's the probability distribution of these two parameters together. Yes, yes. So in the operator language, such that P Q U is replaced by dP dQ du, or you can say d of qp, and f is replaced by f of operator. So in the statistical sense we can say relationship between variables in the classical sense. Now if we have analog of probability with the vis-a-vis the wave function psi as a probability state function, such that psi 0 determines psi 0 q psi 0 psi of 0 q is a complex function. And if we write a psi of qt0, that's the form of psi function at time t0. So d0 qp and psi 0 q determine the probability state of the system, and this determines the physical situation of the system as completely as it's possible in quantum mechanics. We can summarize the derivative relations of quantum mechanics. Means that the complex function psi naught q at time t0, and we should have physical laws which correspond to them. So now you can see, if we in this we have operators associated, the functional dependence of operators to these parameters q and p taken separately and taken together, and the probability distributions which are attached to them separately or taken together. And the functional distributions is somehow seen for this function as a complex function psi, which has this probability distribution. Now we are going to see how we can make sense of quantum mechanical laws with these statistical laws or with these probability distribution, and to see whether a causality can be rescued or restored in whatever form. So that's the point. Can we see, how can we see causality in these alt? So we have to given this, we have this is given. So we have determined probability distributions D0Q and D0P of D0U of every entity concerned at time t. And this is 3, and this is 2. 4 is we have complex function psi t to at time t, and 5 we have probability distribution dtq and dtp of every other entity concerned at time t. So now what we are going to see is what we have said. That's it. So again, we are going to see it. So I'm going to write it in terms of now this probability distribution has written in terms of psi, and now these have to be written in terms of size. So if I write it here, size, we can see psi of tq, psi of parameter q is f operator operating on psi 0 q for dtp q, dtp and dtu. So it's position coordinate separately, momentum separated. It's u, p and q together. In terms of psi can be written as f operator acting on psi of tq, f operator acting on psi of tq, f operator acting on psi of tq. So it's f operator psi 0q, f operator t psi of 0q, f operator t psi of q. So you have to see the role of causal laws in 1 and 2. Roles of causal laws in 1 and 2. Which is playing by, so assuming we are having both time dependent and time independent Schrodinger equation, how can contextualize these probability distributions, their probability distribution vis-a-vis their time evolution or otherwise, because psi 0 q is the complex probability. It's a complex wave which is basically two dependent upon two probability distributions. So the argument here is that since the individual probabilities of two parameters, it's not necessarily equivalent to the individual probability distributions of Q and Q taken together. So if we can dispense this law in probability statements, distributions, if it doesn't hold valid here, it should not hold valid once we apply the same in case of quantum mechanical wave functions psi, or classical statistical considerations. So you can have dp and dq or dpq as concentrated distributions, where this is an f operator operating on q, f operator operating on q. If f operator operating on this pq together, so they degenerate into some function, and it leads to some sort of indeterminacy. So we have arrived indeterminacy in various ways throughout. We have arrived at indeterminacy. So here also we are arriving at indeterminacy. In the last class we just said it came as a basic, indirectly arrived at that it should be taken as a construct to begin with. But here the indeterminacy is arrived at that we cannot equalize the probability distribution of parameters. Two parameters together are not same as if they are taken separately, and these parameters are being operated upon by operators. So the whole class of eigenstates and eigenvalues which you can associate it with those individual parameters separately, they will have different values when taken together, which leads to sort of indeterminacy. So indeterminacy is continuously you use in quantum mechanics. So now here we say the same thing in some different way. So we can say what are you can say whether these we can contextualize them, whether they can be, if you cannot determine things, we can say whether they can be put into the bracket of verifiable statements or not, or these definitions can be verifiable or not. Or in one law we can have a function u as a function of q and p. Then we can have class of equivalent laws. So we can inquire whether interpolation, which is openly left for such a logical liberalism, can be whether we can interpolate q and p and q. The thing is that they are not equivalent to qp. So the question is, if that leads to indeterminacy, so you can start with so it leads to indeterminacy. So we can question whether these statements can be verifiable or not, or we can construct those statements which cannot be verifiable statements as first principles, and whether we can interpolate, whether we cannot interpolate those parameters to their original states. So this all leads to whether one second. This all leads to whether we can have causal chain or not. Causal chain. Causal chain means we go from A to B via causality. But if two parameters, whether it's Q or P, from this to this, from Q0. So if you cannot verify it separately or taken together, so it has some things to say about causality. And we can say that we can talk of probability chains, whether they can be, we can, the precise definition of probability chains, whether we can make a precise statement about probability chains or not. So in that sense, we arrive at something called, so we talk about these probability chains in the context of causality, and it leads to something called anomaly or causal anomaly. Anomaly, a general concept used in physics, but we can say in the sense of causal anomaly. Anomalies vis-a-vis causality is there. So stopping here, we are going to see further details. Next. Okay.